So it's gonna get a little physicky, but um, yeah. So 6 times you exposed to center of mass. I need some props. You wanna teach it then? I'm failing miserably at finding the center of mass of this. Right? What am I trying to do here? Why is it not? Yeah. Oh, here we go. I guess I'm cheating. Wow, this thing is alive. Well, anyways, let's pretend that I just did, right? So here it is. Everything's nice and happy. Oh, look at that. Dan is good at finding center of mass. Now, what if I put a little weight on this end? Yeah, so I'll have to move my finger that way, right? So basically what we can come up with is that the center of mass would to the left, to the left of my finger, whatever the weight I have times the distance should equal to whatever the weight I have here times the distance from the point where I'm trying to balance. So if you increase the weight, you decrease the distance and so forth, right? That's the idea. And this is kind of physicky. But so anyway, so section 7.6, we talk about centroids and moments. So center of mass of a planar plate, lamina. So we know what planar? Well, kind of
Centroids?
lamina. Well, that's the planar, plate. Oh no, there is a lumina. This is a lamina. So basically, because we don't want to get really into physics, so we're assuming we're dealing with, really plates, uniformly distributed weight type of situations, right? And we're just trying to hopefully balance it at some point. I want to find the center. Here we go. Yeah, I'm cheating a little bit, but right. So we're doing this. So it's a very thin, flat, uniformly distributed weight type of situation. So we're looking for some magic point, x bar, y bar, and this is our centroid, we're going to call it. So at the same time, we can think of this as, when we're going to get into more calculus discussions, we can actually think about a curve of a function f. Then we can think about the region bounded by that curve, and we can also find a centroid of that region. So this is the centroid, or center of mass. So what I was trying to do originally, so let's say if I have a stick, and somewhere I'm trying to balance that stick, and I have some weights along that stick. I have this little guy here. Let's call it M1. So location is X1. I have this guy here. Let's call it M2. Location is X2. I have, I don't know, this guy here. M3, X3. And let's say I have this guy here. M4, X4. So again, the products of the distances and the masses will give me um, the location of that balancing point. So in this case, I'll have to take a product of m1 and the distance from x bar to x1 plus m2 and the distance from x bar to x2. That should equal to the product of m3 times the distance from the balancing point and m4 times the distance. And again, they probably should have absolute values for distance, but just in case. Okay. So actually call these quantities, this quantity is called a moment. So how would I say this? How heavily or how drastically all this way trying to rotate the stick around the point where I'm trying to balance it on. So that force, well, not force, but that momentum we call a moment. Okay, but you have the moment on the other side as well. So we want the moments to be equal. So if the moments are equal, then the thing will balance. Okay. So this will be moment 1, and this is moment 2. So the balance will be achieved when m1 equals m2 in this case. Okay? So let me do a simpler diagram. Let me just take something that has just 2 weights. Just to derive a quick formula. So let's call this m2x2. Take it to another page. Okay, so in this case we have moment 1 equals the product of the mass times the distance, so it's x1 minus x bar. I can do it like that just to keep it positive. And m2 would be the mass times the distance, x2 minus x bar. And these two have to be equal in order for the thing to balance. So if I actually set these two things equal to each other, I'll be able to find the location of the balancing point. That's the goal. I want to find that center of mass. So just algebraically, if I do it like that, and distribute the masses, we'll get m1x1 minus m1x bar equals m2x2 minus what? m2x bar.
Is it x1 minus x bar, or like the other way around?
I think.
Because that is the other way around.
Oh yeah, the other side is the other way around. Well, okay, so we'll just do absolute value. So then, let's analyze that. So yes, I need to flip that, right? Because x bar is greater. Okay, so that will flip this order. Or we'll just get the opposite sign, but But yeah, you're right. I should be a little careful.
So, let me ask you another question. Does the whole inside of the formula have the absolute value, or should I just do the x1 and x2?
Well, I mean, we technically has to be absolute value to make sure it comes out positive because we're talking distances. But I mean, in this case, x1 is the way we just drew that. It's bigger than x bar, so that stays positive. In this case, it
I
didn't.
mean, but what I'm saying is, in the event that, let's say that this was on a graph that was on a graph that was you were spanning both sides of the x y-axis, wouldn't the x values have to be absolute? The x bar wouldn't matter, but the other values would have to be absolute to come up with the correct formula.
You mean these values themselves? No, they don't have to be. Because I mean, even if x1 is, you know, on the negative side, when I subtract it, I want it to be positive actually.
Okay.
Because actually I wanted, yeah. So like with respect to the origin, I do want them to preserve the value.
Right.
I just want the distance to come out positive, right?
Right. Will they come out that way if that is an absolute value?
Well, again, the value of a single
Come up with a positive number
for the distance,
for the distance.
right? But the individual value is irrelevant in this case, right?
You're right. I had to roll that through a little bit.
But anyway, so what I want to do, I want us to solve for the balancing point. That's all I'm trying to do, to find the center of mass. So we'll do this algebraically, right? That shouldn't be a problem. It's m1 x bar plus m2 x bar equals m1 x1 plus m2 x2. So I can factor x bar out. And then divide. Right. So the denominator here would be the total mass of the system. And here you have the moments with respect to the balancing thing. So this is just a two-dimensional case, by the way, right? Now, if we go two-dimensional, I mean, it's the same idea. So let's just try. Let's just do the region under the curve right away. See whether we can do that. So, you know, how do we treat problems like this in calculus? Again, if I'm trying to find something that I'm not entirely familiar with, chunk it up, right? What? Yeah, so we're going to take, let's just take one little piece. And let's say, again, this is uh, the region that we're getting under the, I mean, let's say, again, it's not just the area under the curve. So we do get, I mean, in order for us to kind of talk about this, we have to think about the actual weight of that and the distribution of sorts, right? Now, how do you find a weight of an object? I mean, what do? You go, what is it? It's the volume times density, right? Volume times rho equals the mass, right? That would be the mass. Now, well, we're not going to talk volume here. So if you just think, let's just pretend that the thickness of this item is just 1 unit, just for the sake of making math manageable, right? Well, how do you find the volume of this if the thickness is 1 unit? And how do you do the volume? Right? I mean, if you have a blob like that, yeah, so you do the area of the base times the height of 1. So the volume in this case is the area times 1. So that's just the area, right? So this is just to make the math simpler, not to think about the volumes. We'll just think about that the mass of this object will simply be the area under the curve times rho, which is the density of whatever substance we're dealing with. And it's distributed uniformly, just to make math a little easier. So in this case, we'll just think of mass as the area times the density. But I let the thickness to be 1. So it's area squared times 1. So it's, area cubed. Oh, okay, this is what I'm talking about. I have the thingy, the area of the base is 4 and the height is 1, right? What is the volume? 4, right? Well, 4 cubic whatever, right, the cubic units, but the volume, the numerical value, will be the same as the area. Now, so I'm cheating a little bit, okay, because we don't want to get into the volumes. It's getting weird if we get into the volumes. So this is why we're making those assumptions, that we're just going to say, the way we're going to find the mass of that object is just the measure of it times the density. And in this case, the measure happened to be the area. So that's a little logical thing. But yeah, the units of measure for the, for the volume would be the cubic units, but then the units of measure for the density is whatever per cubic unit, right? So they'll cancel anyway. So you get, the mass is just, it's a one-dimensional value, right? So those units will cancel. So anyway, so if I think about this, if I take a strip of this thing, and it's bounded by the x-axis, and I want to find its center, okay? So how we're going to do the center? So if I go in the x direction, again, it's going to be the moments in the x direction around this thing, around the point, over the total mass. Okay? Now, so how do we compute the mass? So let's use A for mass. I'm using mass there. So we agreed that this mass of this strip is going to be the area times rho, right? Now, what is the area of this thing going to be? So the way we're chopping it up, it is delta x, right? And what is the height of that strip? Well, yeah, but I have more, yeah, f of x, right? Because I want to keep it all in terms of x. So the area will actually be, so f of x sub I, whatever the partition is, times delta x times rho, right? So that is the area, I'm sorry, this is the mass of one of those strips. So we'll just write it like this, rho f of x sub I delta x. Now, hang on 1 second. Trying to make sense out of this. Um, so how do we do the, so to do the moment, we'll have to take the mass times the x position, right? This is what we did before. So the x position, again, is just whatever the x position is, right? The x value of this thing would be the, whatever the x was, the x of I. So this will balance it. And then times the mass. And we already agreed, this is how we do the mass times the x. So we're getting rho x of I, f of x of I, delta x.
So is that about here, about the center?
Well, this is the x moment. So really, it's kind of keeping it balanced, almost with respect to the y-axis, right? This is the, well, what is a? Well, yeah, but I mean, but still, like, how do you measure the distance if you just label that? If this is the x of i's partition, right? I mean, the x of I is not reference to a, it's reference to the origin, right? So this is the location of that point. I mean, the a to b will take care of that later, right? Because we'll let the the delta x will be defined in terms of a and b, and when you start adding those rectangles, you'll add from a to b.
So it's the moment of the origin.
But again, like, we just think about this. This is the weird part. Like, if I'm balancing that thing, right? So I'm trying to balance it in this direction, right? And I'm trying to balance it in that direction. Now, what I'm trying to do, so when I'm doing the moment around the x, right? Which way is that balancing? Is it this way, or is it that way? I mean, which one? The first one? Yeah, so you see, so the question is, well, how far is this point, the location of this point in the horizontal direction, right? So what do we use to measure that? Well, I mean, we just use whatever the, the x value is, right? Does that make sense? This is weird too. In my head, it's weird. I'm not a physicist, but. So anyway, but in order for us to do all of them, the total mass, we'll just have to add them all together, right? As I goes from 1 to n. And you add the total moment, you'll add all of this together as I goes from 1 to n. And then this is what will happen. Then the x bar divided by mass. So this is the summation as I goes from 1 to n of rho x of I, f of x of I, delta x over the summation as that goes from 1 to n rho just f of x I, delta x.
Right.
Well, because again, there's a, x sub I is whatever, right?
Yeah.
So I have many of those rectangles. So I'm adding them all together at this point, right? But again, eventually we'll run into infinity. The thing is, rho is a constant, so rho will cancel in this case, right? You'll just pull it out. So rho's cancel, and as n runs to infinity, the x bar x bar will become just the integral from a to b, x f of x dx, over the total mass, which is just simply, in this case, the area under the curve, just f of x dx. So again, the way we really think about this formula, if we let that area, again, we used a for that, a represents just the area under the curve, then you can always think of this formula as 1 over a times the integral from a to b x f of x dx. So this is the location for the x coordinate of that centroid. And this right here, this part, this integral is the moment in the x direction. All right. Okay. Okay, let's do the y bar. Now, also for the y bar, this is actually going to be a little easier. So let's pretend this is that strip, right? So I'm trying to find its center of mass in a vertical position, right? So if the total height of this thing is whatever f of x is, right? Well, where's the center in the vertical direction? Yeah, so it's exactly halfway, right? So it will balance exactly halfway of whatever the y value is. So it's half of f of x times the mass of it, which is f of x delta x, right? And then to find the actual location, you still divide it by the mass. So to do the y bar, so anyway, so we'll do the same way. The moment, if we break it down, the moment in the y with respect to y would be, again, the mass of that, which is rho f of x sub I delta x, times the location in the y direction, which is the half of the height, which is 1/2, and the height is given by this thing. Yeah. So if I rearrange it a little bit, so it's 1/2 rho f of x sub I squared delta x. And then again, we'll just add them together. So you run n to go to infinity, so as n flies to infinity, we'll end up with an integral. Again, the rho comes out. Well, let's keep 1/2 in there for now. So it's 1/2 the function squared dx. So when you divide, the rows will cancel. When you divide by the total mass again, the rows will cancel, so we'll get this formula. So then it's just the integral from a to b, 1/2 the function squared dx over the integral from a to b f of x dx. Which is, again, that's the total area under the curve. So this becomes 1 over a integral from a to b, 1/2 function squared dx. And this is the moment. Well, that's the a, because the bottom part is simply the area under the curve now, right? And I'll give you those formulas on the test. You don't need to memorize them. You'll have the, the centroid formulas. Wednesday, right? Oh, yeah. It's on the syllabus, right? I even printed out some sort of a review package. I don't know why, but I'll play with that. The review packet is multiple choice, but your test is not. Okay? But at least there's answer key on the back. So anyways, let's just do an example. It's deriving these formulas is always kind of weird, but using them will be okay. So I want us to find center of mass and this is just of this region bounded from 0 to 1. So under the curve from 0 to 1, so I'm looking for that point somewhere in there. Oh, there's no, I can do the other page. You mean that part? Okay, well, anyway, so I actually need that. So these are our formulas. The both formulas have this part, it's 1 over A, 1 over A. So we do need to know the area under the curve, period. So we'll just do that separately. We'll do this in 3 stages. We'll compute the area under the curve. We'll set that aside. And then we'll compute this integral, divide by whatever the area under the curve was. And then we'll compute that integral and divide by the area under the curve. So we'll do it in 3 steps. Okay? So you can totally get ahead of me and start computing the area under the curve. Right? That should be all of these integrals will come out pretty straightforward anyways, but the first one, to compute the A, you'll just integrate from 0 to 1, whatever your function is, square root of x dx. So add 1, divide, so it becomes what? 2/3 x to the 3/2 from 0 to 1. Is that right? So you plug in 1, you get 2/3. You plug in 0, you get 0, so 2/3. So then we'll compute the moment, let's say in the x direction. So we get integral from 0 to 1, and then there is x times the function square root of x dx. Which is another integral that we can handle. There's no issues there. It's a Calc 1 problem. So it's from 0 to 1, x to the power 3/2 dx. So you integrate that, you get x to the power 5/2, and then you have 2/5 as a coefficient from 0 to 1. You plug in 1, you get 2/5. You plug in 0, you get 0. So we're good? And we can compute the moment with respect to y. So that's from 0 to 1, 1/2 the function squared. So it's a square root of x squared dx. So that's the other formula. So 1/2 integral from 0 to 1 just x dx after you square that. So it becomes 1/2 times x squared over 2 from 0 to 1. So what do we get?
So how come we're finding the element in the area center going straight to
Oh, oh, you can go straight. It's just because at this point, this is all you have to do now. The x bar is the moment divided by the area. So moment was 2/5, and the area was 2/3, so that's 3/2 times that. So then it's whatever that is, 3/5. Yeah, you can do them at the same
Does
time.
the actual moment mean anything to us without finding out what x bar is?
Well, I mean, it's well, it's definitely a stepping stone, but but I'm sure.
Just throw area from
Yeah, I mean, you can just put the the 3/2 in front of each of those integrals and drag it out. But I don't know, it's easier. Either way, it's okay. Now the other one again is just 3/2 times the moment, so whatever that is, 3/8. So the centroid of this region the x and the y. Well, you don't even need to scroll up. It's just integrals. Computer.
Where does the x come from? Is it
It's part of the formula.
it's just part of the
Yeah,
formula?
it's part of the formula because that's the half.
Right.
Yeah, it's a half of the y value, right? Because this is what we agreed on. You know, the location of this point with respect to the y-axis is exactly halfway. It should split this thing in half. So that's why we do half of the function. Now it looks like we're doing something with an 8, but um, you know, part of the formula right there. Just right there. So the integrals here is actually friendly. The integrals are not bad. Now if we do, so this was an example of something that's bounded by some function and the x-axis. We can do something that's bounded by two functions. Okay? We can look at some region bounded by two functions and see whether we can come up with the formulas. Let's say here is an f and here is a g. So let's say the center of each strip is somewhere in there. So that again, the mass of that will just be the area of that region, right? So those are your denominators. So that will just be, whatever these points are, will be the integral from a to b, the difference of two functions, f of x minus g of x dx, without going into the sigmas or whatever. Right? While the moment would be, the mass times the distance. So the moment mx would be the integral from a to b, x times the same thing, right? The area of that. So it's f of x minus g of x dx. So there are no surprises here. Okay, this is kind of what we expect. The area between two curves. The my is going to be slightly different. Now, if you think about my, because again, the way we did the my, what was that? That was, again, the mass of the object, so that's the difference between two curves, dx. And then it was 1/2 of the y distance, right? So it was really the average between this height and that height, right? We want to find the midpoint there, right? So we're just averaging the two functions in this case. So it's a 1/2 of the sum of these functions. So I'm going to write it here. So it's 1/2. So it's the average of both functions, and then f of x minus g of x. So then with just some simple algebra, we'll get the integral from a to b, 1/2, and then it's just the difference of squares. So it's f of x squared minus g of x squared dx. So this is when we're dealing with two curves. But the rest will be the same. The x bar is the x moment over a, and the y bar is the y moment over a. So the only kind of surprise was that it's not the difference squared, but the square, the difference of squares.
So it's okay to just pull it 1/2 out, right?
Yeah. Is it bothering you?
A little.
All right, let's do this one. Let's do the example. I want us to do the area bounded by, so find centroid of region bounded by y equals 2 minus 2x squared and y equals 1 minus x squared. Now we have to get a little creative on this problem, hopefully. Because what is that second function, the y equals square root of 1 minus x squared? Hey, it's a semicircle, right? So it's between -1 and 1, and then 1 here. So it's a half a circle. Oh, I know what you're talking about. And the other one is what? It's an upside down parabola shifted 2 units up, right? But it will have the same intercept. So it'll be like that. So we're looking for this region. Okay, so first, well, we need to figure out whatever the A is, so the area of that region. So that would be the integral from what? Well, from -1 to 1, but I can do something else. Can I do something else? Yeah. Because we recognize the symmetry with respect to the y-axis, so we can just double everything and integrate from 0 to 1. And we'll do it throughout. Well, I have to be careful. So we'll just have to be a little careful. But, well, actually, we don't have to be careful. But we do. So, well, anyways, you'll see. So it's from 0 to 1. All right, so it's 2 minus 2x squared minus the square root of 1 minus x squared. So I'm just really at this point looking at half of this picture, right? Because again, right now I'm just finding the areas. I'm not looking at moments or anything like that. I'm just finding the area without worrying about anything else. So it makes sense to chop it in half and find half of it and double everything, right? So that's okay. The Calc 1 rule applies. Now, both of these areas, because again, the way the area between the curve works, you kind of finding the area of the upper function minus the area of the lower function, right? And since by observation you can almost say that both of these areas are finite and well defined, right? So the both integrals would exist. So I can actually split it here. I can write it in two separate integrals. So this is what Lynn was saying, that, this is a funky integral, the second one. We cannot really do that one, right? Even if you try the u substitution, it won't work because we're missing. If there was an x on the outside, then yes, sure, life is good. But there is no x on the outside, so we cannot integrate it as it's written. So Lynn was suggesting get all funky with substitutions, which we can, but we don't know what I'm talking about yet. But do we really need to integrate to find the value of this integral? No, because that represents, it's a quarter of a circle, right? This integral, the second integral, represents this area right here. So it's a quarter of a circle of radius 1, right? What is the area of the full circle of radius 1? Well, radius 1. Pi. Okay. So there, the full circle is pi. So what is the area of this? 1/4 pi. So without really getting into the funkiness of integrating this function, we can still come up with a value, right? Keep that one in mind, so we can always do that.
Is that just for this instance?
Yeah, so I mean, well, for other instances, if I just tell you, if somehow you know the area under the curve, well, then why bother integrating? Okay. Oh, I can show you how to integrate. It's actually fun. We'll have time for that. But we'll
If you know how to integrate it, you can also fix derivative. Make an integral out.
Yeah, I don't think I can just integrate it like that. Yeah, I'll have to get, because some of you already had Calc 2, so you know what that thing is heading. But for the general population, we think of this as the quarter of a circle. So that's just 2 times. So I can do the first one. That's 2x minus 2/3 x cubed. Is that right? Evaluated from 0 to 1 minus pi over 4. I'm just going to write pi over 4 there because I know the value of that integral, right? And yeah, that's a totally legal move at this point. It's quarter of a circle. Why bother? Radius is 1. So what is it? It's 2 times, you plug in 1, it's 2 minus 2/3. You plug in 0, you get 0. So it's 2 minus 2/3 minus pi over 4. So that's 4 minus 4/3 minus pi over 2. Right? Do I want to pretty it up a bit? What is it? 8/3 minus pi over 2, right? Or, so it's 8/3 minus pi over 2. And if I really get weird with it, what is it going to be? Should it be 16/3? No, it's a minus, right? So that's 8, so it's 12. But then if I do the over 6, what is it? 16 minus 3 pi, if I wanted to, right? Because we'll have that 1 over it, so we would like to have something that you can reciprocate easily or word like that. Okay. Now, so how would I do x bar? What? Yeah. Now, look at the picture. Look at the picture. Where do you think the location of the centroid, where's the x value of that point? What do you think? 0, right? It has to be on the y-axis. Would you agree with that? Since the whole thing is symmetrical with respect to y-axis and the weight is distributed uniformly, the moment is 0. It's already going to be balanced along the y-axis, right? So the x location is 0. I mean, if I set up the integral, I'll still get 0. Because look, if I set it up with the all proper rules, so mx is the integral from -1 to 1, x times, what was that whole thing? It's 2 minus 2x squared minus the square root of 1 minus x squared dx, right? Actually, in this case, I cannot cheat with the whole pi over 4 thing, but if I distribute the x, I'll get the x outside the square root, so I can use the u substitution, right? Or, I mean, you have a product of this whole function was even, right? This is what allowed us to introduce that 2 before, right? Well, this function is odd, right? And the product of an odd function and an even function is odd function. So the whole thing is an odd function. Now you're trying to integrate an odd function with a symmetrical from -1 to 1. So what are those integrals if you integrate from -1 to 1 of odd functions? What? 0. Provided that the function is continuous, right? Because if I integrate 1 over x between -1 and 1, it's still messy. They don't just, I'm getting into infinity. But anyways, so even if I do it the long way, still with a shortcut, it is 0. But if you really compute that integral, you will still get 0. Okay? And I really don't want to do that. But we could have just said, okay, the thing is symmetrical with respect to the y-axis, therefore the x-coordinate of the centroid has to be 0. So the only thing that we really have to work for is the y coordinate. So if I do the y one, so that will be, okay, Aaron wants to put 1/2 on the outside. That's okay. So we'll integrate from -1 to 1, and then we'll have to square each function. Right? Now again, we're dealing with an even function then. When you're squaring, you have even minus even, both squares still even. So I can do the 2 times thingy, right? So I can rewrite it as the integral from 0 to 1, right? Times 2. Yeah? And then I already have 1/2 up front. So I have nothing in front, right? 2 comes out being greeted with 1/2. You know, they just kill each other. So then it's just the integral of whatever that is. So it's a 4 minus 4x squared plus 4x to the 4th minus 1. I'm doing a lot of algebra. 2x squared minus x to the 4th dx.
Can I ask real quick?
Yeah.
I'm sure it's very simple, but how is mx 0? Because I'm looking at it as it'll be 1 minus a negative, which would be 2 of all of that. Can you integrate? I don't know.
Well, but again, like, do you agree that it's an odd function? Okay. So when you plug in, you know, when you're going to integrate that, you're going to end up with kind of an even function. I'm making up theorems that we haven't proven yet. So that means, doesn't matter whether you plug in 1 or -1, that value will come out the same, and then you subtract the 2 values. So it'll go to 0, right? But even if, you know, we can sit down and work it through, it will come out. But in this one, you know, whatever that is. Oh, yeah, that's a good point. So that's, I messed up on that part. Thank you. So that actually made it easier. Yeah, so yeah, sorry, you're right. There was a square root there, so then it's just minus 1 plus x squared. Okay, thank you.
So 2 times 2 is
Oh, yes, it is h. Wow. Thank you again. So that's an 8 in there. I should have just stopped there. So hey, just compute the integral. Now it's just embarrassing at this point. So it's minus 7. So this is 3. So this is 3 minus 7x squared, right? Plus 4x to the 4th dx. Even in my notes, I just stopped. Now let's keep going. I want to see what the answer is. Is this correct? All right. So 3x minus 7 thirds x cubed plus 4 fifths x to the 5th from 0 to 1. So whatever that is, 3 minus 7 thirds plus 4 fifths. Right? So that's a 15, 45 minus 35 plus 12. Is my math right on this one? So 22/15. Yeah. So then the y bar is 1 over a times 22/15. So 1 over a will be 6 over 16 minus 3 pi times 22/15. Hmm? Yeah, it is. I don't want to see. I want to actually, get some kind of a value. What is this? I can reduce it a little bit, right? So by 3, that's a 5, and that's what, 2? So we get 44 over 5 times 16 minus 3 pi. All right. So 16 minus, that's 16 minus 3 times pi. That's my denominator times 5. Reciprocal times 44. So 1.34. Okay. So this is what we got. So let's do this one. I have a region. Are we still there? We're done with this? So I have a region that's bounded by y equals x, y equals 0, y equals 1 over x, and x equals 2. So I want us to find the centroid of that. So we have y equals x, then we have 1 over x, and then we have 2. This is going to be a little ugly, because anywhere you look, you have to be doing two integrals, right? Because your function kind of changes. Because even in order for me to find the area, which will be the mass, I really have to split it in two. First, I'll do area under x, and then I'll do the area under 1 over x, and I'll just add the two. There's no other way for me to do that. So that will be the integral from 0 to 1 x dx plus the integral from 1 to 2 1 over x dx. Right?
So again, you could actually just see the area of first interval.
Oh, yeah. So it's 1/2, right? Yeah. So yeah, you can do that without computing. This is 1/2 because it's a half a square, right? It's 1, so it has to be 1/2. But this is a simple enough integral. Because even if it's probably even quicker to just integrate them. And the other one is natural log, right? From 1 to 2. So we're getting 1/2 minus ln of 2. Because when you plug in 1 into ln, you get 0. So plus. Yeah, plus. There we go. So now to do the other part, to do the moments, technically we will have to integrate from 0 to 2 x times whatever this curve is, right? Whatever this curve is. So we'll have to split again, right? Because now it's just, it's just the question of the integral. So you have to integrate from 0 to 1 x times x dx plus from 1 to 2 x times 1 over x dx. So we'll have to set this up as two integrals. So that's the yeah. So it's just x squared dx plus from 1 to 2 just dx. So we're getting something out of that. So it's x cubed over 3 from 0 to 1, and then that's just x from 1 to 2. So what are we getting? 1/3 plus 1, right? So so 4/3. So the x coordinate is going to be 4/3 divided by whatever that other thing is. So it'll give us the x value. So again, we'll have to split the integral on the other one. So that will be 1/2 integral from 0 to 1, the function squared, so that was just x squared, plus the integral from 1 to 2, the function squared, so it's 1 over x squared dx. So that's 1/2. X squared becomes x cubed over 3, evaluated from 0 to 1. And 1 over x squared is really, what is the antiderivative of 1 over x squared? Negative 1 over x, evaluated from 1 to 2. So it's a 1/3 minus, you plug in 2, you get 1/2, you plug in 1, you get plus 1. Is that right? So it's 1/2, 1/3 minus, no, plus 1/2. So what is 1/3 plus 1/2? 5/6. So we're getting 5/12. Well, I had a negative 1/2 and a plus 1, so just plus 1/2. So then the x coordinate is going to be, so it's 1/2, right? So it's 1/2 plus natural log of 2, and the numerator is 4/3, so it's 4/3 divided by 1/2 plus ln of 2. So whatever on earth that equals to. I mean, I'm sure I can make it a little prettier, but regardless, it's going to be ugly. So 2 natural log plus, so that's our denominator, right? So then times 4 divided by 3. So 1.12 approximately. And the y bar is going to be 5/12 divided by the same thing. It's not calibrated. I'm hitting division. What'd you get? Oh, shut up. 0.35. You know, with some careful computations, it'll come out to be 0.35. So this is 1.12, 0.35. Whew. Right? Now I have a project for you. Can you take this region and rotate around the y-axis? The answer is yes. Now, can you tell me the volume of that object? Okay, go ahead. Well, why not? I got 20 more minutes. 19 to be exact. Can you compute the volume of region? What? Well, not quite. Well, which method would we use? So slice along the y-axis? Because I want to rotate around the y-axis. So if you slice around the x, you're going to get shells, right? So you're going to do the shells from 0 to 1 on the one function plus shells from 1 to 2 on the other function, right? Let's just do this for fun. So the volume would be, how do we do shells? So it's 2 pi, and then we'll do the integral from 0 to 1, right? So it's the x times the function dx, right? Is that right? Well, you're sure. You're about to be tested on that. So you go the radius times the height times 2 pi. That's how we do the shells. And then plus the integral from 0 to 1, x, no, not from 0 to 1, from 1 to 2, from 1 to 2, x times 1 over x dx, right? Well, right, because it's the height of the shell. Now this integral looks a little familiar. Didn't we have an integral like that? Which one is that? That's this integral, right? Yes. Is that right? So that's 4/3. So it's 2 pi times 4/3. So it's 8 pi over 3. Oh, that was actually a lot easier than I thought it was going to be. I thought it was going to actually take whole 9 minutes to do. 19. But, yeah. But Zach, you were saying something earlier. You had an alternative approach. Yeah, but 2 pi is not just for a circle, right? Because then it means, so what you're saying is, by the way, you have very correct thinkage going on there. So what you're saying is if I take this thing, I rotate around the y-axis, it's 2 pi times the area. But if I take the same thingy, I'll take the same shape, and I'll shift it over here. The area of the shape will stay the same, right? But if I rotate around the y-axis, I'll get a bigger donut, so the volume should be different, right? But if I just keep going 2 pi times the area, then it doesn't matter where the location of this region is, right? So we're missing something. So when you said circle, you said 2 pi, but what else do you need for a circle? Well, but you need a radius, right? Because again, the question is, if you take this area and you start rotating, well, how big of a swing it is. So actually, it's going to depend on the location of the the center along the x-axis. So actually we have this theorem. It's called theorem of Pappus. And this is one of those old BC type theorems, okay, that tells you that the volume created by this, by revolving around the axis will equal to 2 pi times the radius that will be given by, if you rotate around the y-axis, it will be given by the x-coordinate of the centroid times the area. Okay. Now, if I just plug in all the values, we'll get the same thing. Because look, if I take, this is going to be silly, but the volume here is 2 pi times the x-coordinate, right? So the x-coordinate, which was 4/3 divided by the area, right? Because it came out ugly, but it's 4/3 divided by the area. So it's 2 pi times 4/3 divided by the area, but then times the area. So I'm not going to really plug in the natural log of 2 because I know this 2 will cancel. So that's just 2 pi times 4/3. So 8 pi over 3. Right? I cannot prove that theorem. I need some Calc 3 skills to do that.
So, as an example, you could move that out to y equals x, but it would be y equals x minus plus.
You don't really need to think about it. So you just say, well, how about we'll move this point from 0 to 5, right?
Okay.
Whatever the new functions are, it's irrelevant. It doesn't change the area of the shape,
I understand
right?
that, but
So,
change your x bar.
yeah, so then my x bar will be, I think it was what, 1.12, so now it's 6.12.
So that's all you have to do
Yeah.
is add the x value
Right.
to your x bar.
So then I'll just go 6.12 times the area, which was 1 plus, or 1/2 plus natural log of 2 times 2. So this will finally, your dream comes true. We can find the volume of a donut easily, right? Well, what? Didn't you have a homework problem? Wasn't that a pain in the, yeah. So, but now, if you take, a donut, so here's a circle. Let's center the circle. Where do you want to center the circle? 4. And what do you want the radius of the circle to be? 1, right? So then the volume would be 2 pi times what? 4, because the center of the circle would be the centroid 4, times the area of that circle. Pi, right? So 8 pi squared, right? Here we go. So that's the volume of a donut. Well, that donut. If I change 4, it will change the volume of a donut. Or if I change that, it will change the volume of a donut. But now it's easy to find the volume of a donut. I don't know what you're talking about. No. No, you gotta. It's Calc 3-ish. But now, since I still have you here, because apparently these problems take a lot shorter than I anticipated. So, Mr. Lin. So when we were faced with this problem, and this is a preview of things to come after the test, right? You cannot integrate this thing using your Calc 1 techniques or anything else, right? And you might be, even like this thing might come up when you do like the arc length formulas or whatever, hypothetically speaking, because you get a square root of not a perfect square. So things don't, you cannot do the U substitution. Are you with me on that? Your standard, if we had an x outside the radical, good, we don't. So we need to do something in order to fake, to fake the square root out. And the thing that what Lynn was saying is like, well, 1 minus something squared. Have I seen that before? 1 minus something squared. Yes, you've seen something like this, that 1 minus sine squared equals cosine squared, right? You've seen that. We know this is the Pythagorean identity. So what we're going to say, we're going to make the substitution. We're going to say let x equal sine theta, then dx equals cosine theta d theta, right? Just your basic substitution. That's how you do your substitutions, right? All right, so let's substitute. Then if we make a substitution, I'm doing this as indefinite integral because who cares? So that becomes the square root of 1 minus sine squared theta. Then you have cosine theta d theta, right? But then 1 minus sine squared becomes cosine squared, and you have cosine theta on the outside, and then so it becomes cosine theta, right? Which is cosine squared theta, right? And now this one is hard to integrate. We did that one on day 1. We did sine squared. We didn't do cosine squared. Okay. What did you get for sine squared? Very first day of notes you might have taken in this class. Because I don't want to get into this other technique of I don't know if I even saved the notes from day 1. January 12th, probably not. Oh, it is. Probably. Yeah, I need to work this one through as well. Okay, well, anyways, I'm not going to go through the rest of this, but
Well, on the other side of it, it's kind of obvious because of the way that after your semicircumflation is on the origin.
yeah, so it's overkill. But anyways, the way we, again, this is I'm all the way in chapter 8. The way we'll integrate those, you'll replace the square using the double angle formula. You'll integrate that, and then you'll have to resubstitute back. Anyway, so this is all good and fun. Okay, oh, so here's the sort of a big exam packet, and here's the graded homework.
So for limits of integration on that, with 0 to 1, you get 5 or 4.
You can do that. You can convert it, or you just forget about them because you have to just get it back in terms of x and then use the original ones. But yeah, the original ones were from what?
0 to 1.
From 0 to 1, so you go from 0 to pi over 2. Yeah.